mill. It's got hot rolling scale on it. It may or may not have been pickled. And then we have to shot blast it to clean it up. We want to roughen the surface, and then it goes into a spray-on flux. This is a spray chamber where we pass it through that flux. And this is a aluminum tolerant flux. This is a patented flux that is actually a very acidic flux. It's about 1.5 pH. It's got a little bismuth in it to help inhibit things. But that does allow a zinc aluminum alloy to be used, and the flux is then dried, as you see with that induction heater. Now the magic with that is that we are only interested in coating the surface skin, of course. We're not interested in heating up the whole rebar. We don't need to do that. So we put this through a high-frequency induction heater, and the higher the frequency for induction, the smaller the skin depth. So we like using a high-frequency induction heater here because we can heat up that surface to the temperature that's required to dry the flux, which is around 180 or 200 degrees Celsius, and then we can then go directly into the trough, which is allowing the rebar to go straight through. We don't bend the rebar at all. It is a cascade where we pump metal from a reservoir underneath. It comes up into a long pipe through which the rebar is passing. That pipe is kept full of zinc, and it flows out on either side, which protects it from the air outside and allows a length of coating coating section there. And that is enough time, just a few seconds with the preheating of the surface with the induction heating, to allow the complete galvanizing reaction to occur. We then have an air knife on the right-hand side that is an annular ring which blows air on the surface, and we can regulate the coating thickness, and then the product's basically done. It comes out and it's cooled. And we use accelerated cooling where we're coming through a water spray at this point to capture the thickness. Gravity is always with us. We don't want to have a sagging. We want to have a concentric coating. So after going through the annular air knife, we then want to cool that and capture a concentric coating around the rebar. So that's the way it works. So this uses a zinc 0.2 to 0.4% aluminum. We like using the lower end of it. We like 0.2 aluminum because it's got a higher viscosity, which is allowing us to have a higher coating thickness. And this produces a iron aluminide layer, Fe2Al5, iron aluminide, rather than the iron zinc. We don't have the zeta delta gamma as you do in the regular pure zinc galvanizing. We have the iron aluminide. This is a very thin layer, and this allows for the ductility of this coating. And also you can see the coating itself is quite thin. Here we show it's about 10 microns, but we can vary this with that air knife that I showed you before. So this is the aluminum tolerant flux patent. It was granted back in 2006, and this was between Ferrotech and Tech Metals, which is shown as the assignee here, and it is allowing this to be used. And this has been used not only for 0.2% aluminum, but up to 11% aluminum at another company called One Steel in Australia for galvanizing profiles. So the development plan, after having this flux developed, was to work with Tech, the assignee of the patent, ourselves, and Xiamen New Steel, and we designed that line by the middle of 2011. 7 trials were done then. We did have some problems with drossing. We needed to solve those. We came up with a better galvanizing reaction tube into which we were pumping the zinc, and that allowed for the minimization of the exposure of the liquid zinc to air, and we are now very satisfied with the amount of dross that is being made. It's in about the same level as a normal galvanizing process. So right now we're running about 50 microns of coating. It says here up to 95 microns has been produced. I showed you a micrograph before where it was 10. So we have a big range that is possible here, and we're looking at about 50 microns. Back in 2011, we were running a single strand at 1 meter per minute. There was never any problem with the flux. That worked very well. So then, of course, we wanted to go from 1 strand at 1 meter per minute to a much higher production rate. This just shows an example of a typical line design, the one in Xiamen. You can see the entry end on the left side going through the various tanks with the shot blasting and the pickling and then the induction heating, and then the large reservoir on the mid right-hand side, and the pump is in there, and then the tube through which the zinc is flowing in a straight line with the rebar is shown in that larger reservoir, and then the air knife, that little pedestal on the right-hand side, is where the air knife is supported. So the first 7 trials, some examples, we show the entry table here, we show the pump and the single strand of rebar passing through. You can see down here the rebar coming out and of the coating section, and you can see some of the dross we made, which we weren't really too happy about at that point, but we've since solved that problem. In the earliest performance, we wanted to see how it behaved, and so we compared here 3 different things. We have a uncoated rebar, we have an epoxy-coated rebar, and we have the zinc-coated rebar using our process. So this was subjected to 24 hours of neutral salt spray testing, the usual 5% sodium chloride solution, pH of 6.8, which is just about neutral, 35 degrees C. That's a rather normal sort of salt spray test. What happened after 24 hours? On the right-hand side, the very right-hand side, you see the zinc only. So this is the continuous galvanized rebar with about a 20 micron coating thickness in this case. After 24 hours, there's no red rust. It's all white rust. All zinc corrosion products are white. So that's what zinc corrodes, it looks white. There's no red, there's no steel attack. In the middle, you've got the epoxy only, and we drilled holes in this to damage the epoxy intentionally, and you can see the creepage, the under creepage after 24 hours only. You're starting to get red rust and a damage of the paint around there. On the left-hand side, we have the zinc coating plus epoxy, and you don't see any redness in those holes, or a very faint redness in the holes. Certainly the holes in the middle are quite red because of the steel attack, and also, along with the minimal iron attack on the left side one, you don't see really any edge creepage. So this shows the zinc is doing its job. It's protecting the coating from being damaged. So we then went on to do bending tests at Hong Kong Polytechnic University, and this showed that we were able to do these mandrels up to 40 millimeters, and we never had any problems there. And so that's several times the rebar diameter. And then we went up to a 3-strand line. The producer was encouraged enough to work at 3 bars and 10 meters a minute. So that is where we are now. We're running 10 meters a minute with a 3-bar line. And we've gone further then into market development activities, of course, in China. We've got a galvanized rebar standard with the National Standards Administration, and we've been working with the railways and the Department of Housing in China to bring this product and its advantages into those 2 very large construction industries. So this shows an example of the product. This is a 12 millimeter bar showing the kind of bends that are possible with it. And the other thing has been the development of the epoxy coating. We've had a very cooperative partner with Akzo Nobel. They've been able to come up with a epoxy coating process, and we show here some examples. I'll skip this because we're running out of time. If we bend after 1 day, we see on the top that's at 0 degrees C, so this is a low temperature. It's a challenge for the epoxy that we don't have any cracks on the bends. Cracks in rebar coatings can come not only from cracks in the epoxy, but a telegraphing of the cracks through the metal coating through the tension bend on the epoxy coating. And then the lower one is after this is also 1 day after coating at room temperature. We don't see any cracks there. We went out to 28 days because with epoxy you have this aging effect. It absorbs water, and we also see that we didn't have any cracking either at 0 or 23 degrees after 28 days. So we're very satisfied that we have an answer for the epoxy-coated rebar on top of the zinc coating. So we didn't see any problems with these, and that powder has since been shipped from the USA to Xiamen. It's the same epoxy powder that's used for coating the black bar in the USA. So there's no change there. Gerdau has also looked at this. They found no cracking on the bends. We've made a trademark now. We know that if you see the green epoxy, that it's going to be the black bar with the epoxy coating on it. Gerdau is using a yellow epoxy over the thermal sprayed zinc. we are trademarking a blue epoxy. So if you see a blue epoxy bar, you know it's over the hot dip product. So we've trademarked the name Blue Bar. This is available to all of the companies who wish to enter this and make the hot dip galvanized rebar with the epoxy coating over it using this continuous process. So that is now a trademarked mark, and we hope to see this used internationally. So we've started a cooperative program to do further characterization of the product to open new markets. We signed an agreement with the Amoy Technological Institute, which is in Xiamen and New Steel last year. This is the first case study we have. This is a railway project. We have of course, on the railways, they have the cable trays or the cable protective channels, and these need to be made out of reinforced concrete. They're running along the ground, so they can get pretty wet. The top shows the mandrel bending, the making of the galvanized rebar, the continuous galvanized rebar into these bent U shapes. So they first go through the mandrel bending, and there's no cracks on the bends, as you can see from the lower picture. So this is being supplied to one of the contracting companies of the Chinese National Railways. These are then cast into the troughs, these that are holding the cable trays, and they go into place. You can see they're all stacked here, ready for shipment, and they then go off for the concrete casting on site. So this shows another example. This is a pillar cage. This is going to be used in a reinforced concrete pillar. And we're also working in Hong Kong as well with the Hong Kong government on that. There's a lot of public housing there in a very corrosive environment that uses that. The second line is in Dubai. That only began last year. We did a seminar there in November, and that line is now running with continuous process improvement. We are working on a single strand right now, but you can see they're capable of running 8 strands on that line. Also, New Steel in Australia is running these profiles. These are purlins, as they're called, for structural roof applications with 12% aluminum, and that line's running very well as well. So we're undertaking market development activities in several states and provinces in North America with the Ontario Minister of Transportation. They've banned epoxy coatings because of their very unsatisfactory performance. They need to find another answer. So we're promoting the galvanized rebar process to them. We're working with several U.S. states and are working with the Highway Transportation Officials Organization as well on that. And where we wish to, on this, go ahead with education and raising awareness of this new product. From what we've heard about this morning, this seems to be an ideal prospect for India as well. We think this, looking at your projects here, this is a project, a process and product that could be easily adopted. We know the logistics and transportation issues, and we think this could really help out with those. So we're continuing with trying to replicate this processing success now with other producers. And we have our research agenda here, just trying to get more performance data and continuously improving the product as we go. So this just shows there's a huge amount of rebar produced in China, over 200 million tons. So we think if there's 20 million tons that could be coated with rebar, that could lead to 400,000 tons of zinc, which would be a huge new market for zinc if we were to capture this market. We do have a website where most of our information is found at www.galvanizedrebar.com. That has a lot of our performance information on both batch galvanized or general galvanized rebar and the continuous galvanized rebar. So I refer you there for further information. So with that, I'll close.
Thank you, Dr. Goodwin. I must give him a big hand.
Thank you.
He's taken some of my time, but I'm not going to hold that against him. So,
with this, shall we move towards the case study presentations that we have?
Absolutely.
Right. So on that note, ladies and gentlemen, time now for us to have some interesting insights as we present to you the case study session. May I shall first invite the respective presenters. We have amongst us Mr. Vikas Bagar, who is from KEC International, who is an industrial engineer with an experience of 11 years in the field of quality and business excellence. May I request Mr. Vikas Bagar, please come forward. KEC International Limited, it is the RPG Group company, a pioneer in transmission line. Very good. Good evening, rather, Mr. Vikas. Please come forward. Ladies and gentlemen, we have amongst us Mr. Praveen Kumar Mabian. Mr. Kumar is from JSW Steel Operations Head. He is an engineer by profession with 19 years of experience in metal coating and has undergone training program also. He has published various international papers on galvanizing and galvanine, and today he shall be presenting a case study on development of higher coating galvanized material for high durable applications. Ladies and gentlemen, the third case study shall be, it was supposed to be presented by Mr. Raghav Bagri from CD Metal Alloys, but unfortunately Mr. Bagri is not there amongst us. Mr. Bagri, he has extensive experience of 25 years done in the realm of zinc coating at jetty structures, fertilizer storage tanks, conveyor structures, amongst others. He's worked at JK Cement and TVS as well. So he shall be presenting a case study on metallizing, but Mr. Bagri's case study shall be presented by Dr. Frank. So once again, I hand it over to the chair.
Thank you very much. So without further ado, I call on Mr. Vikas Bagar to present his case study. I should remind you also that you each have no more than 10 minutes. Okay, please.
Yeah, namaskar to all of you, and it's a very good and to be a good opportunity for me to be present a case studies of KEC International Limited, which is the pioneer in the transmission line company, not in the India as well as in the world itself. So as all of us are by today's morning, each one of us are basically listen that galvanized bars and galvanized structures are very costly, because the process of galvanization, hot dip galvanization, is a very lengthy one, because a pre-galvanizing process is there as well as past is there. So and basically the zinc, which is the one of the costlier input for any hot dip galvanizing process. So our case study is basically for the optimization of the process and for the optimization of the production with a cost competitive, so that we can serve to the future of the India itself. So first of all, introduction of the KEC. KEC is basically the 1945 established company in an RPG group, basically group companies, and having a turnover of more than 8,000 crore rupees. And we have having a 3 manufacturing locations in India and 2 at the Mexico and Brazil, and total capacity is 2.5 lakhs metric ton per annum. Our the major customers are Power Grid, SNCs, ABB, John Allen, and others overseas customers over there. These are the one of the greatest achievement of the KEC International Limited, the Haldia River Crossing Tower at the Brahmaputra, which is the height of the tower is 236 meter, and the weight of this tower is 1800 metric ton. So by you are assuming how the critical is the erection as well as the manufacturing of the tower transmission for that. So these are some glimpses of the galvanization. In all 3 plants, we have a microprocessor controlled galvanized furnace by Prothom UK as well as the Gimaco Italy, and the other requirements of scrubbers and drying oven and process tanks for that. These are the glimpses of the Butipuri factory, and these are glimpses for our Jabalpur unit in India itself. That's the hot dip galvanizing process, and if you see that one from this is from the quenching, this is the bath one, and prior to that bath, that is a pre-galvanizing process, and after that, that is the after galvanizing process, the bundling and the stacking of that material. So it's a very time-consuming basically process for that. So as an KEC, we have to be, as the market demand is really very high, and we have to capture this particular thing. So we just need to cop up this gap by last year to this year. And for that, we have identified the galvanizing as a pain area, and with the help of the IZA team, Srinivasan sir and other teams, we have done some process improvements in our process. So what is our production? Basically, how we are measuring our galvanizing production. So the galvanizing production is basically measured in the per dip. How many number of dips, how many number of hangers we have galvanized across our bath, and how much tonnage we have taken in a single dip or single bath. So we just do the cause and effect diagram and the brainstorming over there, and as well as we have done the VTR studies, the video time recording studies like industrial engineers are do for identify the value adding activities and the non-value adding activities, and we eliminate all the non-value adding activities so that we can increase our production and productivity. These are the glimpses of the VTRs, the time motion studies over there with the Gilbert and Thublix. And we have reduced this total dipping cycle time. Its average dipping cycle time is around 12 minutes for a whole dipping cycle. It's now reduced to the 9 minutes per dipping cycle. That is the ECRS technique by which we just, some of the activities we are eliminating, some of the operations we are combine and do the parallel, some of the operations we are simplify, and some of the activities we are rearranging so that we can increase our throughput from our galvanizing bath.
You have 2 minutes to conclude.
These are the process of the dipping and unhooking of this thing. Some of the improvements. So actually, in a whole galvanizing bath, we are doing the vertical dipping, which is from one end to the another end. We are not using the whole surface area of the bath. That is a 13 meter length and 1 meter width. So for that, as per the recommendation of the IZA, we are just designing the new design frames, so that we can, optimize the maximum bath, as well as we can, in the galvanizing, the uniform temperature, the variation of the temperature is mitigate for that. So the uniform dipping, uniform material, all the material has been dipped, insert in the bath at the same time, at the same level of temperature. So by that, by VTR doing, we have reduced our dipping cycle from 12 minutes to 9 minutes. So our number of dips improved from 29 dips per shift to 35 dips per shift. Average 600 metric ton productions per month has been increased in the plant. The per dip weight in a dip in a single carrying weight is increased from 0.86 to the 1.17 metric ton. Again, the 30 metric ton per day has been increased for that. And some point of view of the, galvanizing coating, because in a saline weather, where there is a sea coastal area, the galvanizing coating requirement is high, around 130 micron or somehow by 220 microns over there. And in the general requirement, there is a requirement of 87 microns coating, as per the ASTM 123. So for that, for different parameters, this new technology which we have developed in-house, what we have done, we have just collect the whole data of, angle thickness and the angle width. That means the total surface area of a material. And collect, I think, more than 1,000 readings for each and every type of thickness and the section and the length of the material. And we just do the regression analysis and develop this particular formula. As per that formula, and we validate this formula as per the coating requirement of the customers. As per that formula, when we just give the input of the length and the section thickness, what we get the retention time, the actual immersion time when the galvanizing, the zinc coating process has been carried out inside the bath. That is the chemical composition of that thing. So by that, we have developed a standard table, and we just developed this PLC control system and align this PLC control system with our microprocessor controlled galvanizing bath. So our operator just select the toggle switch. By selecting the toggle switch, okay, the material is the 6 meter length and the 12 mm thickness for that. And for that, he has just selected the toggle switch, and automatically the whole retention time and everything has been controlled.
So please wrap up, Mr. Bagar.
And as per the IZA, some process, as the dossing is one of the phenomena where we are just losing our zinc. And zinc ash is another phenomena where we are losing our zinc. And in the means of that, by losing our zinc, that means we are increasing the cost of our galvanizing product. So to meet the customer's requirement and to be the lower bidder in the tower transmission lines, we are improving our process as well as that installation of air agitation system in our pickling and the degreasing process, modification of the drying facility for that. The preflux generation system has been installed, where we are just refine our preflux solution so that the iron content and dross formation can be reduced in the main galvanizing bath over there. And by Taguchi, we are also doing the Taguchi DOE for this standardization of the coating thickness on the special chemistry steel, which, because the base material, that is the steel, is also playing in a very major role in the zinc galvanization and the dross formation for that. So by doing all those things and by installing of the microprocessor furnaces across all the 3 plants, we have optimized our fuel. Our fuel consumption has been reduced from 21 liter per hour to the 16 liter per hour. The production has been increased from 600 metric ton per shift per month. And the galvanizing quality, currently we are working on a 940 WPM galvanizing quality, we are producing that particular quality, as well as by installation of new this dipping cycle, PSC controlled dipping retention time, we are just to be providing the customer within a bare minimum quantity required zinc quantity thickness. Earlier they are demanding 100 micron and we are delivering 300 microns coating. That is the ultimate loss for the company, our organization for that. So by all those things, I say thanks for providing me this opportunity. Thank you.
Please, a big round of applause for Mr.
Within 10 minutes, as told by our chairman. I am going to present a case study on development of higher coating galvanized material for high durability applications. To start with, the JSW is with 14.3 million ton of steel. It's number one company in India as of now, with the highest crude steel producing company. And JSW Steel is a flagship company of JSW Group. Present capacity is 14.3 million tons, and our target is to raise to 40 million ton by 2020. So the first mission was in year 2000, we were 2 million tons. That is 2 by 2K. So now it's going to be 40 million ton by 2020. Focused on integration across complete value chain, right from iron ore to the galvanizing to color-coated products. We are the largest galvanizing and color-coated capacity in India, as well as the largest exporter. We are the first company to get the license from BAEC to produce galvalume coated steel. And recently we have a tie-up with the JFE Steel for the automotive products. Metal-coated production capacity in India is 8.5 million tons. If you see, JSW contribution is close to 25%. This 2.1 million ton, with Tarapur as largest producing coated products in India, is going to reach 1 million ton soon. And there are 11 lines in JSW Group, and 10 lines can produce construction grade with some quantity of OEM. And one more line which is recently put up is auto grade line, which is in Vijayanagar. It's 0.4 million ton and wider width line, it can produce up to 1870 mm width. Now coming back to the case study. See, JSW's initiative was like solar power installation was using galvan coated products in the year 2011-2012. So we visited, our JSW representative visited their solar company and just found out they are just using galvan coated steel. So we just compared what are the benefits of galvan with respect to hot dip galvanized. So in terms of four parameters actually coming to picture, and you can see here, the first one is formability. So existing grade which was used in galvan was 340 MPa grade. So we proposed 350 MPa grade, which is equivalent to EN grade, with the same formable mechanical properties. Corrosion resistance, they were going for a 300 GSM galvan coated product. We proposed 450 GSM galvanized product. And sacrificial protection is at par, so there was no need of any change. So the mounting of solar panel, they were using galvan. So we proposed galvanizing. Why higher coating galvanized material to be used for the solar panel installation? You can see with the increase in coating, your time to first maintenance is going to increase. So with the coating level of 350 to 700 GSM, we could easily achieve the higher life of the installation, and to reduce the total project cost of the installation. This is Solar Rishi. Yesterday some speaker has shown this Solar Rishi mission, Jawaharlal Nehru Solar Mission. And how the product development was adopted by JSW Steel is like in 2012 February, we did some market study, and we took trial with the 350 and 450 GSM coating and executed few orders to OEM. Then we designed the process parameters for higher coating, like we had gone up to 700 GSM coating with existing facilities, not with the new facility. And we have taken line trials with 550 and 700 GSM and executed trial orders. And after getting feedback from the customers, we did some changes in the process. You can see there's a close relation with the designing process parameters and getting feedback. And after that, we have commercialized the steel production. Last year, we have produced 25,000 tons of higher coated products to the solar panel. Now, coming to the technical specification of two dual product lines, Tarapur has got two dual product lines. The CSD3, the first line, we have produced this product, which can go up to 2.5 mm thickness. So earlier, the coating range was